All right, so we're going to continue talking about right triangles, and we're going to talk about some similar right triangles. Now, before we get into any notes or any problems or anything like that, I want to talk a little bit about where these similar right triangles are going to come from. Okay, trying to make this make a little bit of sense here for you. So let's say that I draw a right triangle here. And I want to draw an altitude in this right triangle. Now, the only place that it really makes a lot of sense to draw in an altitude from a right triangle, since an altitude goes from the vertex, and is perpendicular to the opposite side, would be to take the altitude from the right angle, the vertex at the right angle, and draw it to the hypotenuse. And again, if it's an altitude, then it's going to be perpendicular and therefore form a right angle. So, well, before we do this, I think we would all agree, looking at this, there's one right triangle in this picture. When I draw the altitude in, there are no longer only one right triangle in this picture. There's actually three. There's the big blue one, and then there's two smaller right triangles inside of the blue one. There's one here and one here. Okay? Now, I submit to you that all three of those triangles, the big one, the medium-sized one, which might be number 1, and then the small one, which might be number 2 here, are similar. Now, how do I know that for sure? Well, if you remember, angle was a way to prove two triangles similar. Well, I know that all three of these triangles have right angles in them, so they've got one pair of congruent angles already. I just need to make sure that I can pick out some congruent angles out besides the right angles amongst all of these triangles. Now, if you see the big blue triangle, the medium-sized triangle, which might be the medium-sized right triangle, might be this green one, you can see that they share that angle right there. And since they're both using the same angle, they're both going to have an angle that has an equal measure in it. In other words, they're going to have another pair of angles that are congruent. And so by angle, this medium green right triangle is going to be similar to the blue right triangle. Similarly, if I look at this green right triangle, the smaller one, and it's a right triangle because this guy's a right angle, I see the big blue right triangle and the smaller one here share that angle. So by angle, those two triangles are going to be similar. Okay? And because the big blue one is similar to the medium one up here, and the big blue one is similar to the smaller one down here, then it stands to reason that the medium and the smaller one are going to be similar as well. So we've got three similar right triangles here. I can write a similarity statement here. Okay, if I were to label this, then we can come up with a similarity statement. So A, B, C, and label this D. Then I can write a similarity statement that would look like this. There are going to be three triangles in this similarity statement because I've got three triangles that are similar here. Remember what we had to do with writing a similarity statement. Order matters. We want to make sure that the right vertices match up and the right sides match up. So, I'm going to just name the big right triangle, triangle ABC. Okay? Now, to name the second triangle, the second one might be this medium one here. Okay? I'll put an M in here for medium one. I need to match up the vertices. Now, in the big right triangle, B is the right angle. In the medium right triangle, D is the right angle. So wherever B is in the name for the first triangle, I've got to put D in the same place. So D has to go in the middle. Now, since they share angle A, that means A needs to go in the same place in both names. So out here first. And that will just leave, in the medium triangle, that just leaves vertex B out here. So B is just going to go here at the end. Now we can do the same thing for this other guy. Call him little right triangle, L. Okay, right angle needs to go where the right angle goes, and so since in the big right triangle, B is the right angle, that means that since D is the right angle in the little right triangle, then D has to go in the middle again. Okay, but now they share C, and so since C is out here at the end, C has to go here at the end as well. And then it leaves B to just fall in place here at first. Okay? Need to be able to write that similarity statement, right? There's going to be a lot of questions on that. All right. Now, similarity. Two triangles are similar. Or if two triangles are similar, that means the ratio of their side lengths all have to be equal. So if I write ratios of corresponding sides, then all those ratios are going to be equal. So I'm going to start writing some ratios. And I know that they're all going to be equal, so I'm going to set them equal to each other. And the way I'm going to do this, I'm just going to match up from the names, the way I named it. So AB has to correspond with AD. So the ratio of AB to AD has to be equal to, and I can go through all of this, BC to DB, which is equal to AC to AB. Right? Now, I'm going to shorten this a little bit. I'm not going to write ratios between the two smaller triangles. I want to keep writing it between the big one. The big one and the smaller triangles, right? So now all of these are going to be equal to the ratios I can write between the big guy and the smaller guy here. That means AB to BD has to be equal to BC to DC, and it has to be equal to AC to BC. Okay? All of those ratios are equal. I can pull out and write a proportion. I can pull out two ratios, set them equal, and make a proportion. If I were to do that, there would be some interesting circumstances here. Okay? And I think to see all of the interesting circumstances, we're going to have to go ahead and write the ratios between the two smaller triangles. I didn't think we were going to have to, but I think we are indeed, actually. So let's do that. So the ratio of AD to BD has to be equal to, let's see, DB to DC, which has to be equal to AB to BC. If none of this makes any sense and you are just super curious, then you can come talk to me during STAR and we'll go through it. In the end, I'm just trying to set up the theorems that we're going to talk about. Okay? Now, I can strategically choose some ratios to set equal to each other. I'm going to pick, let's see, this one and this one. This proportion that's already right here. This proportion already has the same length, the same segment in this up diagonal. So it's going to have the same number in this up diagonal. You have to think for a second. But what that means is that, if you remember, this is how we found the geometric mean. We put the same number in the up diagonal, and we put the other two numbers that we're trying to find the geometric mean of in the other diagonal. So AD and DC are different. In other words, some of the segments in this picture end up being, the length of those segments end up being the geometric mean of some of the other segments in this picture. That's where our theorems kind of come from. And there are more in here in all of these ratios, and I would pull them all out, but I want to conserve some time here, so I'm not going to do that. But I wanted to let you know that the geometric mean, that these proportions that we're going to start writing from these theorems, do come about from similar triangles and matching up the sides from those triangles. Okay? That being said, without any further ado, let's get into what you want to put in your foldable. Right? In the next page in your book, we're going to write in the similar right triangle theorems. Okay? So the similar right triangles. And the first theorem involving similar right triangles says this. It says that the altitude of this right triangle is the geometric mean of the pieces of the hypotenuse. Now, What does all that mean? Well, when we see a picture like this, when we see this big right triangle with an altitude drawn through it, it's going to be helpful to recognize that, or to look at this picture in two different ways. You can either see this picture as a big right triangle with an altitude drawn through it, or you can recognize the fact that there's actually three right triangles and work with the three right triangles. And there are going to be times where you're going to want to think of this picture as one or the other. You're going to flip-flop back and forth. The theorems are written in terms of this being a big right triangle with an altitude drawn through it. Okay? If we do that, if we draw a big right triangle and draw an altitude through it, then what we know is that the altitude is the geometric mean of the pieces of the hypotenuse. Okay? All right, well, what does that mean? That means, and I wish I could kind of cover these up for a second, but I'll just mark them out. Okay? That means that the theorem says I can set up a proportion to help find a geometric mean. So I'll create a proportion, two ratios equal to each other, make my fraction bars in my equal sign. And since the altitude is the geometric mean, that means I'm going to put the altitude in both places of the up diagonal. The altitude here is BD. Okay? So that means I'm going to put BD in these two, and the two spots of this diagonal. You have to think back to us doing geometric mean before. Okay? Now, it's the geometric mean of the two pieces of the hypotenuse. When you draw this altitude in, it hits the hypotenuse and it creates two pieces, there and there. So when we talk about pieces of the hypotenuse, that's what we're talking about. Now, the altitude is the geometric mean of the two pieces of the hypotenuse. So I'm going to put BD in the up diagonal, and what I put in the other diagonal is AD and DC. Okay? That's what we mean by the pieces of the hypotenuse. Okay? So we can write this proportion right here. And that's going to be true all the time. The length of the altitude will be the geometric mean between the length of the pieces of the hypotenuse. Okay? Now, this theorem is kind of called the T-theorem. And it's called the T-theorem because when you write your proportion, if you were to follow it along in order of how we wrote the proportion, we would go down AD to get to BD. Then BD comes next in our proportion. Then BD comes next in our proportion. And then DC comes next. And so you create this T. Those are the pieces that you're going to use for this proportion, the T. I think T makes enough sense to try to find. That's going to be your pattern. Okay? So, as a quick example of this, we're going to look at this. So let's say we want to find the altitude. The altitude is x, right here. And we know that the length of AD is 10, and the length of DC is 4. Okay? Well, if that's the case, then I know from this theorem, and you're going to have to remember the theorem, the altitude is the geometric mean. So I'm going to stop right there, and I'm going to make a proportion, and I'm going to put the altitude length in the up diagonal. So here's my proportion. I'm going to cover these up again. I'm going to make a proportion, and then since the altitude is the geometric mean, then I'm going to put the altitude in the up diagonal. The altitude is x. So I'm going to put x in this up diagonal. And it's the geometric mean between the pieces of the hypotenuse. And the pieces of the hypotenuse are AD and DC. So 10 and 4. So 10 and 4. Now I have a proportion that I can cross multiply and solve. X times x is x squared. 4 times 10 is 40. Square root both sides. Reduce down your radical to get 2 radical 10. Okay? That's going to be the length of the altitude. All right? Now, as you see, I've written the similarity statement here. And you really ought to try to get to that similarity statement yourself. Okay, I may cover up the next one. I'm going to do another one here in just a second and make you write the similarity statement for that one. Okay? But triangle ABC is similar to triangle ADB, which is similar to triangle BDC. And we kind of went through this already. So It may not make a lot of sense to try to come up with a similarity statement for this triangle. All right, but that's the altitude theorem. We'll do some, well, let's stop real quick and take a look at a couple of examples on how to set this up and let you try. Okay? In your example packet, well, you actually don't have these examples in your example packet. So in your example packet, if you want to write these out in the margin or find some place to write these out, it's going to be helpful. I don't want to get into the first two examples in section 7.3 just yet. Okay? But draw in someplace this triangle here. Okay? Try to write the similarity statement for that triangle, and then go find x. I'll give you a couple of seconds to give it a shot. So stop the video, try to figure it out, and then start it up again and see how you're doing. Okay? All right. How'd you do? First, the similarity statement. All right, in this first line, I'm going to name the big right triangle. So I'm going to call this ACD. Okay? Now, C is the right angle. B is going to be the right angle for both of the two smaller right triangles. So wherever C is in this name, which is in the middle, I got to put B for the other guy. So B is going to be in the middle. And that's going to be true for both of them. So I might as well put the B in there for both of them. Now, middle triangle here, this guy right here, shares angle A with the big guy. So since A is in the beginning, it's in the first spot of the name of the big triangle, I'm going to put A in the same spot here. And that just leaves C to fall into place. Now, for the same reason, D is at the end of the name of the big triangle, and since the big guy and the small guy both share angle D, I got to put D in the same spot, which is going to go here. And that means C has to just kind of fall in line to go right there. Okay, so there's your similarity statement. That's what you should have come up with. All right, now, at some point you're going to have to figure out, well, anyway, we're going to have some more proportions we can write, and you're going to have to figure out which one to use. For right now, I'm going to go ahead and just set up the altitude theorem. The altitude theorem, the T theorem, which says that the altitude is the geometric mean. So I'm going to stop. I'm going to create a proportion. And I'm going to put out the altitude, which is x, in the up diagonal. Now it's the geometric mean for the pieces of the hypotenuse. And the two pieces are here and here. So 10 and 9. Now we can cross multiply and solve. X squared equals 90. Square root. And so x is 3 square root of 10. So the altitude length is 3 square root of 10. Okay? It's that simple. Hopefully you find that simple. Example number 2. I'll give you a second to draw that in. Maybe go ahead and get started with both the similarity statement and the solving for x. Okay? This is what you should have gotten. There's your similarity statement. ONM is similar to OPN, which is similar to NPM. Now, if you didn't name the first triangle ONM, that's okay. You can switch those around. But bottom line is the N in the big triangle has to be matched up with the P in the two smaller ones. Okay, and we walked through how to match these up. The M and the N need to match between the big and the medium, and so on and so forth. So as long as yours match kind of like mine do, then you're in good shape. Okay? Now the altitude theorem says that the altitude is the geometric mean. So I stop, I set up my proportion, and I put the altitude, which is 7, in the up diagonal in both places. Don't have to put x in the up diagonal every time, but the 7's here. That's the altitude. And the altitude is the geometric mean of the two pieces of the hypotenuse. So it's the x and the 98. Okay? All right. And then you cross multiply and solve, and x ends up being 2. Okay, I hope that makes enough sense. All right, let's move over to the other theorem. Okay, in the bottom half of your page here, you're going to want to write in the other theorem. The other theorem deals with the legs. It says the leg of the right triangle is the geometric mean of the whole hypotenuse and the adjacent piece of the hypotenuse. So a little bit different. Okay, we've got to break this down a little bit. So we're drawing our triangle here, x, y, z. Drawing our altitude, y, w. Okay, and when we do that, you should be able to come up with this similarity statement. You really ought to try it before you just write it down. But the similarity statement should look like that. And here's what we're going to get into. The leg of the right triangle is the geometric mean. Now, in a right triangle, how many legs are there? Now, hopefully you're saying there's 2. So we can actually write a proportion for either leg. Okay, so we're going to end up with 2 proportions here. So anyway, the leg of the right triangle is the geometric mean. So stop. We know what that means. We write a proportion, and we put the leg in the up diagonal, in both spots of the up diagonal. Now, for the first one, we can use leg xy. That means xy is going to go in this first diagonal. Okay? Now, in the other diagonal, we need the whole hypotenuse. So this big right triangle's hypotenuse is what we're talking about. Remember, these theorems are written in terms of this big right triangle. So the whole hypotenuse is xz, and the adjacent piece of the hypotenuse. Now, remember, adjacent means next to. Since I'm doing this proportion for this leg, then I need the piece of the hypotenuse that's next to that leg. And the piece of the hypotenuse that is more next to that leg than the other one is xw, is this one right here. Okay, they touch. So it's the adjacent piece of the hypotenuse is the piece of the hypotenuse that touches the leg that we're working with. Okay? That's your first proportion that you could write. Now, since it has another leg, we can always do it from the other one. The leg of the right triangle is the geometric mean. So this leg here, stop. Write a proportion, and in the up diagonal, put the leg, yz, in both spots. Okay, here and here. Now, it's the geometric mean of the whole hypotenuse. Again, the whole hypotenuse is xz. And the adjacent piece, now the adjacent piece moves. And the piece that's touching this leg is this guy right here, wz. So that's why wz is right there. Okay? This is sometimes referred to as the swoosh theorem. And that's because if you were to trace out the proportion, you kind of get a swoosh. I don't know. I think it is easier to see for the second proportion where xz equals yz, and then yz equals wz. So you kind of get this, I don't know, it kind of looks like a check mark or a swoosh. It's not as easy to see as in terms of a pattern as the T, but it's there if you want to try to use it to help you remember what parts go where. All right? Otherwise, memorize the theorem. All right, so a quick example of this might be, if I want to find this leg here, yz, and I know that this piece is 11 and this piece is 9. Okay? All right, so the leg is the geometric mean. So I stop and I set up a proportion. Right? And I put the leg in the up diagonal, x. Now, it's the geometric mean of the whole hypotenuse, which is 20, which is why you see a 20 here. And the adjacent piece is the piece that's touching the leg, which is this 9. Okay? Then you cross, multiply, and solve. X times x is x squared. 20 times 9 is 180. Square root both sides, and you get 6 square root of 5. Okay? So the leg is 6 square root of 5. But it works that way if we're going to try to write this for a leg. All right? All right. Let's try a couple. Okay? In your note packet, in your example packet, you do have these problems. Okay? Skip example 1 and 2. We're going to skip the rock climbing wall example for just a minute and work on these guys. Let's do these guys. Okay? All right, let's set these up. Now, we know we're going to use this leg theorem. So for this first guy, we could try to write the proportion for this leg right here. But it's not going to make a lot of sense because we don't have anything written in there for that leg. We don't know what the length of it is, and we don't really want to know. So it's not going to make a lot of sense. We're going to write the proportion for this leg. And so the theorem says that the leg is the geometric mean. And so I stop. I set my proportion up. And since I know that the leg is the geometric mean, I'm going to put the leg in the up diagonal. X goes here and here. Now, this should look familiar. It's the geometric mean of the whole hypotenuse. The whole hypotenuse is all of this, which is 20, and the adjacent piece. The adjacent piece to this leg is this piece that's 9. Okay? It's the one that's more next to it than the other piece. We cross, multiply, and solve. Okay? Just like the ones that you just put in your foldable. All right? All right. Try to write the proportion for the next example. Stop the video, set it up, and then stop it or start it again and see how you did. Okay? Did you set this up? The leg is the geometric mean. So this leg that we're going to do this for is this guy right here. So 6 goes in the up diagonal of the whole hypotenuse, which is 12, and the adjacent piece, which is A. So that's why the proportion looks the way it is. Okay? Hopefully that makes enough sense. Okay, now we're going to try the last example here. So again, stop the video, give it a shot, and start it back up again and check your answer. Okay, did you get this? B is 25 over 6. The leg is the geometric mean, the leg is 10. So 10 goes in the up diagonal of the whole hypotenuse, which is 24, and the adjacent piece, which is B. Okay? So hopefully you've gotten a feel for what these theorems say and how to set these proportions up. Now, let's go take a look at some examples that might pull in both of these. Okay? In your example packet, you've got these first two examples here. Okay? Take a shot at writing the similarity statement for each. Well, I'll go ahead and write these in, and you can see if you can see them, get to them later. So it should be EGF is similar to, let's see, H goes in the middle here, H goes in the middle here. Then we put E here and G here, and then we put F here and G here. Okay? So that should be your similarity statement. All right, so find the value of X. Now here's the trick. You're not going to know which theorem to use necessarily right off the bat. So my suggestion to you is to set up every proportion. The one for the altitude and then the two for the legs. And then solve the ones that you can in succession. Now ultimately we want to find this X. Okay, so the first thing I'm going to do is set up the altitude proportion. The altitude is the geometric mean. The altitude is X, so X goes in the up diagonal. And it's the geometric mean of the pieces of the hypotenuse. Well, I don't know what those pieces are. So I can let this be Y and this be Z, and so I'd be putting a Y here and a Z here. But I can't solve that, obviously. So let's go to the leg proportions. And I'll do it for this leg that's 3 first. The leg is the geometric mean, so 3 goes in the up diagonal, of the whole hypotenuse, which is 5, and the adjacent piece, which is Y. Now I can cross multiply and solve that. And so Y is equal to 5 over 9. Okay? All right? Now, I know what y is, so I can plug in y here. Y is 5 over 9. So I'm going to make this 5 over 9 over x equals x over z, which is kind of weird. That's okay. Let's go write the other leg proportion, right? The leg here, 4, is the geometric mean, so 4 goes in the up diagonal, of the whole hypotenuse, which is 5, and the adjacent piece, which is z. I'm going to cross multiply, get 5z equals 16, or z equals 16 over 5. So now, and for this z, I'm going to put 16 over 5. Now I'm going to cross multiply this proportion because all I have is one variable. X times x is x squared. If I multiply 5 over 9 and 16 over 5, look at what happens. The 5's divide out, and I'm left with x squared equals 16 over 9. Now we got to square root both sides. And so x is 4/3. The altitude is 4 over 3. Okay? Hopefully that makes enough sense. Okay? Try setting up this last example, example number 4. Stop the video, see if you can't come up with x, and then start it back up and see how you do. Okay, so this should be what you got. So x should be 60 over 13. Okay? There's a lot of work there. Not a lot of things that are too brain taxing as long as you know the theorems. So the altitude is the geometric mean of the two pieces. That's where this came from. The leg is the geometric mean of the whole hypotenuse and the adjacent piece, and that's where these two came from. So make sure you go through that and understand. If you don't, come see me during STAR and we'll walk through it. Okay? Oh, by the way, I made a mistake over here. I found it while I was working the other one. This guy right here is a mistake. I got to go back through and fix it. This is definitely 9. So y is equal to 9 over 5, which means that this is 9 over 5, which means that some of this is going to change. So sorry about that. So x squared is going to be equal to 9 times 16, which is 144, over 5 times 5, which is 25. Square root both sides, and x is equal to 12 over 5. Okay? All right. All right. I think it is helpful also if we see a quick use for this. Right? So to find the cost of installing a rock wall in your school gymnasium, you need to find the height of the gym wall. Okay? You use a cardboard square to line up the top and bottom of the gym wall. Your friend measures the vertical distance from you to the gym wall. Approximate the height of the gym wall. So here's the picture of what's going on, right? So they're using this cardboard square so that we can see all the way up to the top of the wall here and all the way down to the bottom of the wall here. So that we have a right angle right in here. And the distance from you to the gym wall can be represented by this segment from your eyeballs to the wall. And then the distance from you to the floor is your height, right? So this is 5 feet right here. All right, so that's where this picture all came from. And we want to find the entire distance of the wall. We want to find this whole thing, right? Well, we already know that this piece is 5. We just got to go find this piece W. Well, we know that this guy right here is the altitude, so we're going to use this altitude theorem. The altitude is the geometric mean, so 8.5 goes here, and 8.5 goes here. And it's the geometric mean of the pieces of the hypotenuse, which is just this W and 5. So that's how you're going to want to set that up. Now it says approximate the height of the gym wall, so you're probably going to end up going ahead and typing in the square root button function in your calculator and getting a decimal answer, one of the few times you want to do this. So cross multiply and solve. 5 times W is 5W. 8.5 times 8.5 is 72.25. Then we divide both sides by 5, and we get 14.45. Okay? So a quick use for this. All right. Hopefully that made enough sense. That's it. Your homework is out in Canvas. Make sure you take a look at that and get submitted before class starts. Okay?